Let's talk about what it means to draw a graph. We do it all the time. Every time we get our hands on a new graph, one of the first things you do is you try to draw a picture of it. And you can get a lot of information about a picture. You can quickly look at things like, you can look at degrees quickly, if it's a small enough graph to draw, and you can start to see other structures in it. You can look for other patterns in the graph just by looking at it. And so it's a useful, handy thing to do. But you can also think of the drawing of a graph as a formal mathematical object, as like a real set of points in the plane that you've drawn. There's actually a way of drawing each curve that you, when you move the pen from one vertex to another. And it turns out to be very useful, interesting, and worthwhile for us to talk about this kind of formalism of drawings of graphs. So what does it really mean to draw a graph? Here's what I think is perhaps one of the best examples that comes up like almost immediately when you start drawing graphs is this example of drawing K4. And I'll show you what I mean. Is that, okay, if I draw 4 vertices, I'm going to connect them all up. Okay, and I could draw it like this, right, where I cross these 2 edges. But you know, I could also kind of move this one somewhere out here. Let me do it in a different color. I could have drawn this edge around the outside. And then I would have had no crossings. And you see that there's somehow differences between these 2 drawings. You know, or I might even be able to draw K4 with all straight lines. Right? So again, now once you can talk about what it really means to have a drawing of a graph, you can start to classify and characterize the different kinds of drawings. And you can also start to talk about what kinds of graphs admit what kinds of drawings. And so that's what we're going to do. All right, so let's warm up with an example. I like this example a lot. It comes up in combinatorics, and it looks like this. So if I take all permutations of 3 elements, now there aren't too many of these, right? There's just 6 different permutations with 3 elements, and I'm going to say they are adjacent if they differ by swapping adjacent elements. So I'm going to write them like this. Okay, so I've got 0, 1, 2, 0, 2, 1, 1, 0, 2, 1, 2, 0, 2, 0, 1, 2, 1, 0. Okay, so those are my 6 permutations. I listed them here in lexicographic ordering. And if I'm going to say, okay, if they swap adjacent ones, I guess these 2 have to be adjacent because they swapped the second one. I guess when I did this, you can see that the first thing is the same. So these 2 swapped and these 2 swapped. And now swaps of the first 2, so things that end in 1, things that end in 2, and things that end in 0. Okay, so there it is. Okay. So I've kind of drawn these arrows. A much maybe nicer way to draw it, something like this. Let's draw it like this. 0, 1, 2, 0, 2, 1, 2, 0, 1, 2, 1, 0, 1, 2, 0, 1, 0, 2. And when I say nicer, well, it's nicer because now I see that actually I know this graph. This is just C6. So it's isomorphic to a cycle on 6 vertices, which I could probably have picked out of this, but it would have taken me maybe a little bit more work. Okay, so that's like a drawing, and by drawing it, I get some sense of it. And so what did I do? I put the vertices in positions and places in the plane, and I drew the edges as curves. Okay, let's do a more exotic one. Let's do permutations of 4 elements. This is super hard. In fact, I'm going to need a finer pen here just so that I can fit them in. I kind of know that I'm going to have 24 different permutations, right? Because there's going to be 4 factorial equals 24 different permutations. I could put them into 4 groups based on who their first element is. So let's just start like that. If I was going to write them in lexicographic ordering, let's do it like this. 0, 1, 2, 3, 0, 1, 3, 2. In fact, let me write 6 zeros here. And I'm going to get these the 6 permutations, the other 3 elements. 2, 1, 3, 2, 3, 1, 3, 1, 2, 3, 2, 1. Okay, and also know what at least in just this subset of 6, I know that this should look like a subgraph isomorphic to C6, because we just did the permutations of 3 elements, and that's really what we're seeing here. So we're going to see some cycle in here, like this, which will look something like that. So, and they all start with the 0. So this was, let's go start over here, 0, 1, 2, 3, 0, 1, 3, 2, 0, 3, 1, 2, and 0, 3, 2, 1, 0, 2, 3, 1. Hang with me here. Okay. All right, so I know that at least this is a subgraph, and then I've got, for instance, the permutations that start with 1. Let's write those. I'm just doing these lexicographically again. It's the easiest way to remember that you get them all. Okay, and again, there's going to be a cycle of these. But first, let's also just see where there's adjacencies among these. So obviously, they have to have the swaps here have to be a swap of the first 2 elements, because everything in here has a different first element than everything in here. And the only way to do that is to swap the 0, 1, right? So these actually are the only 2 edges between these. So if I were to draw this, I know there's going to be another cycle of size 6 here. I know it's going to be another cycle of size 6, and it's connected to these like this. Okay. And just by symmetry, actually, you can work out the rest of what this will look like. It's going to be squares here as well. There's going to be my other 2 hexagons, right? So these are all the ones that start with 0. These all start with 1. I have all the ones that start with 2 over here, all the ones that start with 3 over here. And then I need more connections, actually. So, so between these, I'm going to have some connections like this, over here, and over here, and over here. And actually, what's fun, I think, is you can look at the structure of this and recognize, or even just ask questions about what these other objects you see mean. So I've managed to draw it with no crossings, which is pretty cool. It wasn't immediately obvious that I should be able to do that. But I was able to draw it with no crossings. And I see that there's some other cycles here of size 6, right? There's these 6 cycles here. And if I were to work through all of these, I think what would happen was this would be 1, 0, 3, 2. And this would have to be 1, 0, 2, 3. So each vertex has degree 3. And that makes sense, too, because the degree is, well, I can swap the first 2 elements, the middle 2, or the last 2. So I get this edge by swapping the first 2. I get this edge by swapping the last 2. So I must get this edge by swapping the middle 2. So this is 1, 3, 0, 2. Okay, as I go around here, this is going to be 3, 1, 0, 2. And this will be 3, 0, 1, 2. Okay. And so you see these all end in 2, which makes sense, right? If I do all the permutations that end in 2, I'm going to get 6 of those permutations, and those also form a nice cycle of size 6. So you can see that these other 6 cycles correspond to all the permutations that end in a particular value. And there's one other 6 cycle you could easily miss, which is this outer one, which also corresponds to cycles. I guess it would be cycles that end in 1. I'm sorry, it's permutations that end in 1. Whew. Okay, so I do this as an exercise mostly just to show that when you come across a weird graph, you start to draw a picture, you try to figure out a good drawing, and a good drawing can start to give you other insights into the structure. In fact, there's other cool properties of this. This can even be realized in 3 dimensions as a nice convex polytope. It's called the permutahedron. And so we'll get to see some examples of things like that, hopefully later in the course. All right. But to really get into talking about what it means to draw a graph, we're going to have to talk about topology. And there's 2 main things that we're going to get from topology. We're going to get some notion of continuous functions, and really what is a topological space? And so these are the two main concepts that we're going to have to work with here. And I think continuous functions, everyone has seen, but there seems to be a widespread confusion about what it actually means for a function to be continuous. Let me just highlight this important fact, is that we're not doing calculus here. Somehow, a lot of, at least high school curricula in the US, managed to confuse a lot of students about whether or not you need derivatives to be continuous. We're not talking about smooth functions, we're just talking about continuous functions. And this is going to capture the idea for us at first of kind of putting the pen down, moving it without picking it up, and stopping somewhere else. So we're going to get curves like this. And we're going to think of curves, even curves that cross themselves will be continuous. And as I said, right, we don't care about smoothness. Right, so we're going to look at continuous functions, and we're going to try to understand them in a more general setting of topological spaces. Now, when you have a topological space, really the main thing you get from this definition is some notion of open sets. So if you have a reasonable notion of open sets, then you have a topological space. And reasonable here means that, well, the union of two open sets is open. The intersection of two open sets is open. The entire space is open. The empty set is open. And actually, just any arbitrary unions of open sets are open. So if you have those conditions, then you have something called a topological space. And in this class, even though this is a huge field that includes lots of different examples of topological spaces, in this class, really, we're just working with the most familiar one. We're just talking about Rn. Right. In this case, you can say that X, a subset of Rn, is open if it is a union or finite, it's basically constructed from unions or finite intersection of open balls. Right, and a ball here is just the set of all points such that the distance from X to some center is less than or equal to the radius. Oh, I put less than or equal to. That would be a closed ball. This is strictly less than the radius. So it doesn't include the boundary, is the open ball. Okay, so this is the definition of what it will mean to be an open set in Rn. We're not going to have to use it too much, but at least I want you to have seen it at least once. The important thing about having this notion of open sets really is that it's what defines continuous in the first place. So you may have seen some like epsilon delta definitions of continuity, but a really general notion of what it means for a function to be continuous is just the following, right? So a function from x to y is continuous, where x and y now have to be topological spaces. So we have to be able to say what's an open set here and what's an open set here. But it's continuous if for any open set in y, its preimage is open in x. So preimages of open sets are open. This is the short one-sentence definition of continuity. Okay, and in pictures, this is like, if I take let's just take some closed curve here in the plane, and let's look at a point here. I can have a function which maps, say, this point over here, this point over here, and let's say it maps everything else to just this curve. So it squashes this curve, this closed curve, into a line, into this curve without a loop here, to this path. Right. So this could still be a continuous function. What I would do is I would look for some open set here, right? So the open sets in the image are just intersections of the open set in Rn with the curve, and I look at where it came from with some open set here, and I just want to make sure that the preimage of this open set is open. And since I can take the union of two open sets as open, like if I look over here, I might see, two pieces in the preimage, and again, that's okay, right? So the union of two open sets is still open, and so again, here's the end. So I have these, if I look at any open set over here, I kind of pull it back, look at the pre-image, and ask, is it open? And if that's always true, then the function is continuous. Okay, so mostly we're going to use some kind of standard continuous functions, and then we're going to build things from them. So for instance, here's some of the most simplest kinds of functions that are continuous. So first of all, the identity function on set, this is continuous. All right, so it shouldn't be too surprising if you take any open set in X, the pre-image under the identity is just that set itself, which is open by definition, so it satisfies the definition. So just from using the definition of continuity, it's immediate to see that identity is always continuous. Also, if I have two different continuous functions, I can compose them and get a continuous function. Right, so this is good, right? This means that we have those two important things, which are identity and composition. Right, we saw this with sets. We saw this with graphs and graph homomorphisms as well. It's really important to check. All right, and here are two examples that you probably, of kinds of functions you've seen, which are clearly, maybe I won't even say clearly. I'll just say they are continuous. So constant functions, right, this is one of the easier cases. It's one that, like for instance, if I have a function from x to y such that f of x is just equal to some particular point. Right, every x in x maps to a particular point c and y. And you can check this as well, right? If I have some open set in y, then the pre-image of S is equal to one of two things. It's either equal to X, that is the entire space, if my special point was in that set, or it's equal to empty otherwise, right? And these are both open, right? The definition of a topological space required us to put the whole space and the empty set as open sets in there. So these are both open, so we saw that the pre-image now of an open set is open. All right, so that's for constant functions is sort of the most, maybe perhaps the most trivial kind of function you can write. This was supposed to print in color with my little asterisk here. Linear functions, and the fine print, if you can read it, says finite dimensional vector spaces, right? So when you talk about linear functions, right, we're talking about functions of the form where they have the following property, right? F of a plus b should always be equal to f of a plus f of b, and you have to be in a vector space so that it makes sense to talk about what we mean by addition. And Rn, of course, is a vector space. So these kind of linear functions, as long as we're in finite dimensional spaces, then these functions are also continuous. I won't prove that here, but I guess I should also just point out that also affine functions like this, which you may have seen, like f of x equals mx plus b, right, where there's some extra additive term here. These are also continuous. These are obviously very simple examples of functions, and they're much weirder things, but we can get really far in the constructions we use just by working with linear functions. All right. I pointed out that we had some closure under identities and composition. That is, if we have continuous functions, identity functions are continuous, composition of functions, continuous functions is continuous. And when we have those two things, we always end up with this kind of isomorphism. And so the definition here for topological spaces, that is isomorphism for topological spaces, is called homeomorphism. So it has a new name, but you can think of it just as, again, isomorphism in the case of topological spaces. And the definition is exactly the same as almost every other one we've seen. Let's see, I shouldn't say almost. It is actually exactly the same as the definition we used for isomorphism of sets and isomorphism of graphs, right? So in this case, two topological spaces, x and y, are isomorphic or homeomorphic. We'll write it this way. If, again, we have functions f and g, and these, of course, have to be continuous functions, because when we talk about functions between topological spaces, we're only ever going to be talking about continuous functions. And they have this property that their compositions are identities. So if I go round trip from x through f and g like this, so g compose f, it should give me the identity on x. And f composed with g should be just the identity on y. Okay, so these two functions, f and g, are the homeomorphisms, and x and y are said to be homeomorphic. All right, let's work out a very simple example. So here I've got a square and a circle, and they're empty, right? It's just the boundary. So it's just as the curves here. I could do this also with them filled in, but let's just do just the boundary here. I claim that the square and the circle are homeomorphic. So I need some function, right, that maps x to y, and a function that maps y back to x. And what I'll do is I'll just consider the origin to be sort of right here in the middle, and I'll use a projection. So what I'll do is I'll just draw a line like this coming out. And so if this is a point x, I'm going to map it to this point. We'll call that f of x. Okay, so the inverse of this, right, if would be going the other way. If I have some y here, this point here will be g of y. And we could check that these two functions are continuous. And then we would check that the composition of f with g, that is if we go from x to y, f of x here, and then back via g, we come back to the same point. Okay, so so even though squares and circles are geometrically different, they're topologically equivalent in this pretty strong sense of what we call homeomorphism. And you've probably seen other maybe jokes or silly examples of this where people talk about how the topologists can't tell the difference between their coffee cup and their donut. And the reason, of course, for this now is that the coffee cup and the donut, assuming that there's just the one handle here, that there's actually a homeomorphism between these, and that somehow you would be able to rearrange or move this thing around in a continuous way to be exactly the same shape as the donut. Pulling out the inside and stretching the handle around. And you can imagine doing this. And this is kind of the sense in which topology captures connectivity information, things about holes and pieces that aren't specific to the geometry. And that's going to be useful for us.